Welcome to this video on a significance test for a mean. By the end of this video, you should be able to perform the four-step process for a significance test about a population mean and understand the connection between confidence intervals and a significance test. So today's scenario is, for many years, doctors have told people that normal body temperature is 98.6 degrees Fahrenheit. So today, let's find out if this is true. So we took a sample, and I took a sample of 32 people. So our N is 32. I got a mean temperature of 98.13, and I got a standard deviation of 0.822. Okay, from those 32 people when I ran one variable statistics on this. So do the data provide convincing evidence that the mean normal body temperature is different than the doctor's claim? Assume the conditions have been met. So we're not getting into checking our conditions. We're going to assume that they've been met. So take a minute, pause the video, and let's answer the state portion, and then we'll move on from there. All right, well, let's see how you did. So it does say take the temperature of 32 people. Think of our class as an SRS of all high school students. So we're saying that our population is all high school students. So when I define my parameter mu, I'm wanting the true mean body temperature of all high school students. The statistic came from our sample. That's the 98.13. Now, for our hypotheses, it says, do the data provide convincing evidence that the mean normal body temperature is different? That word different, that's not less than or equal to, or greater than. That means not equal to. Okay, so that means our alternative is a non-equal to. So our mean, our mu of our null hypothesis is, that's what the doctor's claim is 98.6. But our data, it suggests something different, but they don't care about direction. They want to just know about different than. So we have not equals to 98.6. It doesn't say anywhere in there about what alpha level we should use, so we're going to choose 0.05 because that's the most common one to use. Okay, so the name of this procedure, we have a one sample t-test for mu. Well, and we can write mu. You don't have to spell it out for mu. So the general is, it's just what are you looking for? We need to find a test statistic. And to get that statistic, we're going to take the statistic from our sample minus the parameter and divide that by the standard error is really what we've got to think about what we're doing here. So the formula that we need to use, it's very similar to finding the z-score. It's the t-score instead. You want to take your statistic minus your mu and divide it by, to get the standard error, remember you take the standard deviation of the sample and divide it by the square root. Okay, so I would like you to take a second and set up your specific work, plug everything in, get your test statistic, and then we'll work through the rest of that part together. All right, so let's take a look. So we're going to draw our picture. Remember, we got a t-score, and our t-score is actually negative 3.23. So this is a t-distribution, not a normal curve. Okay. So because we standardize, that means our mean is going to be at 0, because whenever you get a standardized test statistic, you get a mean of 0 and a standard deviation of 1. And we got a test statistic of negative 3.23. So we want to know this area. However, we didn't just ask for the less than. Remember, we said different. So we want to know that's negative 3.23, so we're going to use the symmetrical properties here. And we want to know about 3.23 and above also. So we're really wanting to know both of those areas. So what we're going to do is we can, on our table B, if that's how you're going to work this, we need to look at our t-distribution. So this is a sample size of 32, so it would be a degree of 31. If you're using the table, 31 is not on the table, so we're going to use the degree of freedom of 30 because that's what's on the table. If you're using the calculator, you can use 31. We'll look at the calculator in a minute. So we're going to use, so on line 30, we're going to go and find as close as we can to 3.23. So on line 30, we're going to go across, and 3.23 occurs between these two values. So if we follow them to the top, we have a tail probability of 0.001 to 0.0025 to 0.001. Okay, so we're going to go, let's put them in order. So 0.001 to 0.0025. Somewhere in there is our p-value, but this information is only telling me one of these sections. We have two of them, so remember previously when we multiplied this by 2, so we would get a complete t-value for both sides of these of 0.002 to 0.005. So somewhere in this p-value is our true p-value for this problem. Okay, now let me show you how to do this in the calculator so we can make a comparison. So we're going to go to Stat, over to Tests. We're doing a t-test. Okay, our mean was 98.6. That's our null. Our statistic from our sample was 98.13. We had a sample standard deviation of 0.822, and we had a sample size of 32. And for our alternative, we had the not equal to, so you need to make sure you take care of this here. And when I tell it to calculate it, there's our t-statistic, negative 3.23, and I got a p-value of 0.0028. So let's take a look at that on our paper. So when we look at that, the 0.00289 does in fact fall into this interval. So when you put it into the t-test, it multiplies it by 2 for you, so you don't have to. So now what I want you to do is I want you to take a moment and write a good conclusion and come back and check to see how you did. All right, let's see how your conclusion went. Assuming that our null of 98.6 degrees is true, there is between a 0.002 and 0.005 probability if you looked on the t-table. Otherwise, you can say a 0.00289 by the calculator of getting a sample mean body temperature of 98.13 or lower, or 99.07 or greater, purely by chance. Now those numbers, remember, our null was 98.6. We got a sample of 98.13. So that should say 98.13. So what I did is I said, how far apart are these? And I applied the same distance over here because the distribution is symmetrical, and that's where the 99.07 is. So we said 98.13 or less, which is what we have shaded, or 99.07 or greater, which is what we have shaded. That's where those numbers came from. Because both 0.002 and 0.005 are less than alpha, we're going to reject the null. Okay, we have it's a very small chance of this happening purely by chance. So we do have convincing evidence that the mean body temperature is different than the doctor's claim. Okay, and interestingly enough, there's been research that's come out recently that says, in fact, 98.6 is probably too high anymore, because when the norm for temperature was made originally, there wasn't as good health care. Antibiotics were not a thing. People were sicker and they tended to have inflammation and problems for a longer period of time, which raises body temperature. But now there's less of those issues because of medicine. And so the true body temperature is probably closer to 97.7. So that's kind of interesting that our data was able to support that. Now, what we're going to do is we're going to take, I want you to make sure you got your calculator. We're going to look at another class's results. And we're going to do a t-test on this class also. Okay, so we're going to go into your stat, over to your test, down to the t-test, because that's what we're performing. Our null hypothesis is still the doctor's claim of 98.6, but this class got a sample statistic of 97.9, so we want to change our x-bar to 97.9. They got a standard deviation of 1.6, and they had 30 people. So we can do that. They're still going to use the two-sided test because we're just saying, is it different? We're just seeing how they compare to ours. And we're going to calculate. So they had a t-score of negative 2.39 and a p-value of 0.0232. So their p-value here is 0.0232. That's probably enough decimal places to give us a good idea. Now, what does this mean at different alpha levels? So 0.0232 is less than 0.1. So that would lead to a rejection at the alpha 0.01. 0.02 is less than 0.05. So that would also lead to a rejection at 0.05. At 0.01, 0.0232 is greater than that. So here we would fail to reject. So we're not going to reject at that alpha level. Now I'm going to tie this to the intervals that we did in the last unit. I'm going to show you how to do an interval on the calculator too. It's pretty handy. So we're going to go back into stats, over to test, and we're going to do a t-interval right there. Number 8 in mine, it could be different in yours. So a t-interval. Okay, we're going to put our statistics in. So the sample statistic was 97.9. The standard deviation was 1.6. And our sample size was 30. So we want to look on our intervals. So a 90% confidence level is at alpha 0.1. So this is alpha equals 0.1. Because to find your confidence level, alpha level, we do 1 minus your, whatever your confidence level is, what alpha is, how they come up with alpha. Okay, so a 95%, and there's your 5%. So that is alpha equals 0.05. And this is alpha equals 0.01. Okay, so these two complement each other to add up to 1. So we want to have a 90% confidence level, so I'm just going to change that from 99 to 90, and I'm going to tell it to calculate. And it makes my confidence level, my interval for me. Now, I would only use this to check my work because it can get kind of, you know, especially in a test situation, you have to show all the work anyhow. And you guys have practiced so much that you do just as well working it out by hand. But, so I have a confidence interval here of 97.404 to 98.396. So 97.404 to 98.396. Now, would you reject the null with this confidence interval? The null is 98.6. 98.6 is not in that interval. So yes, I would reject there. So we're going to take this and we're going to run it again. Go to tests, go to t-interval. And instead of 90, we're going to go and make it be 95. Tell it to calculate. It gives us an interval this time of 97.303 to 98.497. 98.6 is still not in that interval, so we would reject. Okay. And then our last time, back down to T interval. This time we're doing a 99% confidence interval. So we're going to change that to 99 and get a confidence interval of 97.095 to 98.705. Now 98.6 is in that interval, so you wouldn't reject at that point. Okay, so we've talked about the plausible values and how it relates to our hypotheses, but now take a look. What connection do you notice between the answers in 1 and 2? So the decision really whether or not to reject is the same using confidence intervals for a two-sided test. So let me say that again. The decision whether or not to reject the null is the same using a confidence interval or a two-sided significance test, because the two-sided test, when you draw it, you have shading on both sides. Your confidence interval is what happens between those two shadings. Okay, that's your plausible values between the two shadings. So that's how they're related. And we have talked through that actually quite a bit where you guys already understand the relationship, but I wanted to make sure I pointed it out here. All right, let's flip this over for a summary. All right, for your four-step process, when you have your four-step process in your state, make sure you define your parameter and state your hypotheses. You'll want to include your alpha level in that also. In your plan, make sure you name your procedure, check your conditions, and remember your conditions are random, 10%, and normal, and we've discussed multiple times about the 3 stages of normal. For the do section, make sure you have the plugged-in formula, your test statistic, and the p-value. Make sure you have your drawing that's labeled also. And in your conclusion, you're going to interpret the p-value. That's the assuming the null is true statement. You need to make a decision about your null hypothesis. That's reject or fail to reject. And then you need to make your conclusions about your alternative, whether we do or do not have convincing evidence for the alternative. And everything has to be in context there. Okay, so it's really the same things I've been saying all along. Just make sure that we include all of the pieces. All right, and then when we have a confidence interval and a two-sided test, if your null value is in the interval, that means your null value is a plausible value and you would have to reject the null. Fail to reject the null because it's possible to get it. If your null value is not in the interval, that means the null value is not a plausible value. That means you need to reject it. And to find your confidence interval and how it relates to alpha is alpha equals 1 minus whatever your confidence level is for a two-sided test. So if I had a 87% confidence interval, my alpha would be 0.13. They complement each other to add up to 1. All right, hopefully that was helpful. Let me know if you have any questions and I'll see you in class.
Yeah.